If you recall, we've been talking about partial derivatives. We've got a function of two variables, and we described two derivatives. If z is f of xy, then we've got fx of xy, or dz dx. And this is the derivative of z in the x direction. And then the other partial derivative, fy, or dz dy, that's the rate of change of z in the y direction. This was the new thing for us because before we only had one direction. Everything was with respect to x or with respect to t. There was only one input, so we only had one derivative. We didn't have to think about it that much, but now we've got two. We've got an x direction and a y direction. And then we start thinking about where we are on the xy plane and think, well, there are way more directions than just x and y. The good news is, even though we haven't had linear algebra, we know that everything in that plane can be described as some combination of x and y. So everything in this plane can be described as a combination of x and y. So the good news I have to write good news a lot because I got to find out how long it's going to take me to stop reading and or at least thinking the words good news without thinking of Futurama. We're not over it yet, so. So everything in the plane is a combination of x and y. So what we're going to do is take how z is changing in the x direction, how z is changing in the y direction, and we're going to turn it into some its own direction. We're going to make a vector out of our two partial derivatives. Everything is a combination of x and y. I know how things are changing in the x direction. I know how things are changing in the y direction. We just need to combine those two. We're going to create a vector out of our two partial derivatives. Create a vector out of our two partial derivatives. This vector is called the gradient of the function. We're talking about the gradient of f. This is a vector that we're going to build out of the partial derivatives of the function. We're going to start with just the two partial derivatives of the function, but once you see how we build it, it's not going to be hard to make a gradient out of a function of three variables, or even just an equation in three variables. That's it. I don't know if that sentence came out how I wanted it to. I'll check the replay and edit it, even though we know that I won't. So the notation for the gradient of f. This is the gradient is an operation that we're going to apply to a scalar function. So we're going to call it gradient of f. We're going to note that this gradient can be evaluated at all kinds of different places. So the gradient of f at xy and if I was going to force you to take the two partial derivatives and build a vector out of it, the gradient is exactly the vector you would just decide to build. We're going to take the partial derivative with respect to x and put that in the x direction, multiply by I. Then we're going to take the partial derivative with respect to y and stick that in the y direction, multiply it by j. So it'll just be fx at xy I plus fy at xy j. If I told you to make a vector out of two partial derivatives, and I kept using the word direction, this is the vector that you would have come up with. Question? This right now is for two variables, but we can adapt this to a function of three variables, and there would be I, j, and then a k. So this is another way that I could just ask you to find the two first partial derivatives of a function. That's mechanically one of the things that we can do with this. So as a teacher, you're going to try to make it sound super important that to be able to calculate gradients. And then eventually the students will be like, oh, dude, are you just asking us to do more first partial derivatives? Like, oh, yes, but I'm asking in a different way. There is going to be some kind of change in z that's going on. So we're going to have to interpret this because we're thinking about we're going to be imagining this from a top-down view. We're going to imagine a contour diagram of our surface, and we're just looking at the top-down view, and then we'll decide what the gradient is going to be telling us. So for example, let's say f we're just going to recycle our old one that we used before. Let's find the gradient of this function. So for the gradients, we need two first partial derivatives, fx at xy. It's going to be 3x squared y to the fifth. And fy at xy is going to be 5x to the third y to the fourth. To build the gradient, we just take these two partial derivatives. Take the x derivative in the I direction. And the y partial derivative in the j direction. The way we're going to use the gradient in a plane is that we're going to be imagining looking at a top-down view of our surface, of a contour diagram of our surface. we're going to be thinking about the gradient of f in the plane when we're looking at a contour diagram of the surface. So let's think about what the gradient is going to be telling us. How are we going to interpret the gradient? So we're going to think about what this gradient is going to be telling us. And we're going to do this through example. Why complicate things? So let's think about this plane. Z is 5 when x and y are 0. And we're going to go through 0, 0, 5, and we're going to tilt down with a slope of -2 in the x direction, and we're going to increase with a slope of +3 in the y direction. So we can imagine this is just a plane. Let's start with something familiar and see what the gradient is going to tell us. So first of all, let's calculate the gradients. Let's find, oh, I wrote z and not f, so I'm going to have to write dz dx. The partial of z with respect to x is just -2, and the partial of z with respect to y is just 3. So our gradients, I'm going to the function. Our gradient of f will just be -2i plus 3j. We're not surprised by this in the least. We know we're dealing with a linear function. Linear functions have constant rate of change. There's a constant rate of change. No surprises here. A linear function, constant rate of change. Also notice that the gradient is constant. I have a constant rate of change in the x direction, a constant rate of change in the y direction. So our gradient is constant. That's going to make it easy to draw. So Let's think about what this function looks like from a top-down view. When z is equal to 0, we get 5, I should have gone with 6. We get 6 minus 2x plus 3y. I'm going to edit it to make it look like I had 6 the whole time. I'm not, but when I first wrote the 5, I'm like, oh, dude, you don't want 5, you want 6. I'm like, oh, 5 will be fine. 2 times 3 is 5, it'll work out. And then it took me this long to realize that 2 times 3 was in fact not 5. I need a voiceover. So in the movie version, when I write the 5 here, it's like, oh, it was only then that Professor Leach realized that 2 times 3 was in fact 6 and not 5. So I just changed it. So we're going to have a line with a slope of 2/3 and a y-intercept when z equals 0, a y-intercept of 2. So here, if we rewrite this, we'll get y is equal to 2/3 x minus 6 divided by 3, which is 2. So we got -2, a slope of 2/3. Here's our z equals 0 contour. Now we know that the contours of this plane are just going to be a bunch of parallel lines. Let's figure out how far apart to put them. So if z equals 1, that's going to make this, that's not going to be convenient. I'm going to need to divide by 3. So I'm going to make the next one what's happening at z equals 3. Because I'm going to be dividing by 3. So I got 6 minus 2x plus 3y is equal to 3. And at this point, you're like, oh, dude, can't you just do this arithmetic in your head? I'm like, oh, no, not at this time of the morning, not on this day of the week. Friday and Monday are not days to just try to do arithmetic in your head, especially at 8 o'clock in the morning. I have not had enough coffee because there isn't enough coffee to really, for me to process arithmetic. So we got to figure out what's going to change about the function so I know how far apart to put this. But I knew I wanted a 3 because of all these reasons. So y, notice that we're going to get the parallel lines because we're still going to take a 2 and then divide by 3 for the x. But now I've got a 3 minus 6 is -3 divided by 3 is -1. So this one we had a y-intercept at 0 or at -2. So now our y-intercept is at -1. Now we see what the pattern is going to be. We can see what's going to happen. I'm going to make these lines all 3 units apart for z. So I need to go up 1 more, and that'll give me the z equals 6 contour. What we want to get out of, did I miss? I missed. Let's draw sketchy. What we want to notice is that in general, the z is increasing as we go this direction. And in the x direction, we see that, in the y direction, we see that z is increasing. because of course it is. And we see in the x direction, z is decreasing. If I go in the positive x direction from here, I'm headed towards a lower z value. So we can see that this is sloped up in the y direction, but down in the x direction. And if I drop down 1 here, here's going to be z equals -3. Here's where z equals -6. It's not just the fact that these are parallel lines that makes this a plane. The fact that these parallel lines are evenly spaced and the z values that correspond to these parallel lines are the same distance apart. So at any point, let's draw the gradient. So the gradient is -2 in the x direction and 3 in the y direction. So I'm going to draw the gradient, -2 plus 3. I can pick any point because it's always the same because this is a plane. I'm taking it easy on myself. But from this point, if I draw the vector -2, +3, that's the direction of my gradient. What do we notice about the direction of this gradient?
Perpendicular.
Yeah, the gradient is perpendicular to the contour. The gradient is perpendicular to the contour. Here's a way we can interpret the gradient being perpendicular to the contour. So first of all, we've done exactly one example where the gradient is perpendicular to the contour. And then so you're just going to have to believe me because, you know, we've only got like a 50-minute class to deal with this. The gradient will always be perpendicular to the contour. That's one of the things that we want to recognize about the gradient. The gradient will always be perpendicular to the contour. The gradient is perpendicular to the contour. Notice that the gradient is pointing where z is increasing. In the direction of the gradient, z is increasing. So the gradient is perpendicular to the contour. The gradient is pointing in the direction of increase. We also want to notice the gradient is pointing in the direction where the surface, the values of z are increasing. The gradient is telling us the direction of maximum increase. The gradient is pointing in the direction of maximum increase. We could think of this as the steepest path up this plane. So if you're standing on this plane and you want to go up by the steepest path, you run perpendicular to the contour. Why does it make sense to go perpendicular to the contour for the maximum increase? Well, what happens if we run parallel to the contour? How much is our z increasing? There is no increase. That's where the contour comes from. That's where z is not changing. So this makes sense because if when we think about running parallel to the contour, when we are parallel to the contour, tangent to the contour, z is not changing. That's where the contour comes from. That's the curve where z is not changing. So no change along the contour, no change in the direction of the contour. I didn't have enough space to write in direction of. I punted and wrote along. There's no change in the direction of the contour. So perpendicular is the change, is the direction of maximum increase. If I want the direction of the maximum decrease, what direction would that be? If we go in the opposite of the gradient, that will be the direction of the maximum decrease. So if we look parallel to the contour, our z is not changing. That's the path that we should go if we want to not go up or down the hill. The maximum decrease, we will turn perpendicular to that for the steepest path up the hill. The steepest path down the hill will just be turning the other direction. So I've got a direction. So if I'm parallel to the contour, I got zero change in z. If I'm perpendicular to the contour, I've got maximum change in z. What kind of factor are we going to get for the stuff in the middle? What are we going to multiply by to get the stuff in the middle? How are we going to go from zero change and parallel, maximum change at the gradient? What's that factor going to be? So parallel, no change. perpendicular max. If we go in the direction of the gradient, that's going to be our maximum change. If we go perpendicular to the gradient, that's going to be no change. Oh, I should say parallel to. Let me reframe this from the gradient perspective. I just said parallel and perpendicular, and that was not specific enough. Because I have two things here. So. Perpendicular to the gradient, we might say tangent to the contour. Now is the part that I had messed up. Perpendicular to the gradient is tangent to the contour. The gradient direction is perpendicular to the contour. That's why saying parallel and perpendicular was trash. In the gradient, we have the maximum change in z. Perpendicular to the gradients, we have zero change in z. So gradient direction, max change in z, our factor is 1. When we're perpendicular to the gradient, there's no change in z, our factor is 0. If we are 0 degrees off the gradient, we have max change in z. But if we are 90 degrees off the gradient, it drops down to 0. 0 degrees gives us a factor of 1. 90 degrees gives us a factor of 0. 0 degrees is giving us a factor of 1. 90 degrees is giving us a factor of 0. Moreover, if I go negative 90 degrees, the other direction, I'm down to a factor of negative 1. That's the opposite direction of the gradient. So there's additional information. Opposite gradient. That's going to be your minimum change in z. That's going to be a factor of negative 1. Just going to multiply that by negative 1. Oh, and that could be like that's 0 in the other direction. So well, that's not 0 off the gradient. That's 180 off the gradient. So let's call that 180 off the gradient. Yes. No, you aren't confused. You are spot on. You might be confused, but you are spot on. Cosine of 90 is 0. Cosine of 0 is 1. And what's the cosine of 180? Negative 1. So the factor that we're going to be doing, if we go from, when we want to go from factor of 1, and that drops down to 0, the factor that we're going to be using is cosine. And where are we going to get the cosine? You said the other part of it. The dot product. If I want the derivative, the rate of change of z in some direction other than the gradient, I just have to figure out how far off the gradient that is. And for that, all we need is a dot product. Because the dot product is saying, the dot product is multiplication at an angle. And so we just want to know, since gradient is maximum change, I want a factor of 1 for 0 degrees, so that's cosine. And if I have 90 degrees, I want to drop down to 0 because at 90 degrees off the gradient, we're running parallel to the contour, running in the direction of the contour, and the contour is built by things not changing. So the factor that's going to show up is the cosine, and it is going to come from the dot product. So this information says cosine, and cosine says dot product. So if I want to know how z is changing in some weirdo direction, I figure out the gradients and I take that weirdo direction. I say, how far off the gradient is this weirdo direction? And the way we figure that out is with the dot product. That worked out great. You need to think about this more. This is why I do this one on a Friday. So I can introduce the idea of a gradient and say, this is how we're going to get at the derivative in whatever direction we want. Normally I leave it at this, but someone said, hey, that's a dot product and a cosine. I might go, well, shit, yeah, that's it. And now off you go. Think about that. We'll come back on Monday and we'll talk about the derivative in some particular direction. That's going to do it for today. That's going to do it for this week. I'll see y'all on Monday. Everybody have a good weekend, and thanks for playing.